Hi, it's time for the lecture number 3, and the subject of lecture number 3 is linearization and small signal model of PWM converter. In the last lecture, lecture number 2, we derived the average model of PWM converter. So in this lecture, we'll linearize the average model and will develop the small signal model of PWM switch. This is the eventual goal of this lecture and the next lecture. But in this lecture, we'll focus on this linearization, and the following lecture will cover the small signal model of entire PWM converter. Okay. So this is the recap of last lecture. In the previous lecture, we derived the small signal model of PWM switch and the small signal model of PWM converter. So first consider this. This is buck converter, and this is the switch model representing the actual circuit configuration of buck converter. So we have active switch here, passive switch, and the inductor is located here. This is A terminal, this is P terminal, this is common terminal where the inductor is connected. And we defined this combination of this active switch and the passive switch, PWM switch. And the PWM switch is connected, the common terminal of PWM switch is connected to the inductor. So in here we have 3 terminal cell, and this 3 terminal cell is the central part of all the PWM converters, and this is the buck converter. If we rotate this combination of this PWM switch and the inductor by 120 degrees, you will obtain the boost converter, and another rotation will produce the buck boost converter. So we take this procedure using this buck converter, but result can be extended for the all 3 basic converters and all the isolate converters derived from the basic basic PWM converters, and we will discuss the details about that later. Okay, so this is the switch model, and we consider this. This is the step input change. The input voltage was at high value and step down to low value and stay here and come back to the higher value again. And this is the conceptual representation of inductor current, ILT, and this shows the triangular ripple of the inductor current with this purple color. So actual switch model, cycle by cycle simulation will generate this purple waveforms. Okay. And this is the average model derived from this model. Okay. Inside of this is PWM switch model. We call it PWM switch model. No, this one. This part is PWM switch model. Average model of PWM switch, that is the difference from the PWM switch model. So I got confused previously. So this is the average model of PWM switch. So this combination of active switch and passive switch is converted with this ideal transformer based on the averaging process we discussed in the last class. So we have this ideal transformer, and in this ideal transformer, this terminal and this terminal are always connected to this single point, and the turns ratio of this is 1 to dt. dt is continuous duty ratio. In the switch model, you have QT. This is the actual switch drive signal, which alternates between the value of 1 when switch is connected and the value of 0 when switch is opened. Okay, so we perform this average process. This is the moving average of this value of the switching function Q2, and the average of this is called continuous duty ratio. So all the variables here, circuit variables here, the Vs and this, and every circuit variables are continuous variable. Even this duty ratio dt is something like this. So it contains a DC component, and the AC component is superimposed on the DC component. So this is the average model. Again, this is the average model of PWM switch, and the box in the black curve is average model of 3-terminal cell. Okay, so by simulating this, and we'll obtain this yellow curve. So yellow curve is exactly following this envelope or time average value of mean value of this purple color waveform, which is cycle by cycle simulation with triangular type ripple component, and this generate the smooth waveform following this average value of this. Okay, this is the meaning of the average value, average model of anything. So this is a time invariant, but this is the nonlinear circuit model, because, for example, this voltage across this is the P terminal, this is common terminal. So voltage between CP terminal, VCP bar means average variable. Something similar to this is product of this. This is also time varying variable. So it may contain the DC component and the AC component, namely the DC bias, AC signal, and the multiplication of this dt is also time varying variable. So product of two time varying variables generated this process is a nonlinear process. So this model is time invariant, but it is a nonlinear model. So we should linearize this to obtain the small signal model of converter. So if you apply the linearization process and you apply this S-domain conversion, then you will obtain the small signal model of PWM converter. And we are using buck converter as an example, but this procedure is equally applicable to any PWM converters. Just the concept of this 3-terminal cell and rotating these things. So this is general discussions, and this is all of this is the review of the previous lecture, and this we have glimpse of the current lecture, upcoming lecture. So in this lecture, we'll discuss the linearization of nonlinear relationship, something similar to this. Okay, this is the nonlinear expression, and we want to have some linearization process applied to this to obtain the small signal model of this. Okay, so first we discuss the linearization process of nonlinear relation. So there are three different interpretations for the linearization. First one is based on the truncated Taylor series expansion, and second one is the concept of the local slope of nonlinear curve, and the third one is perturbed expansion of nonlinear expression. They look different, but all of them are equivalent. Of course, they generate the same result, and conceptually they are the same, but this maybe you may feel there is some difference. Okay, so but they are equivalent. Okay, let me explain this first. This is a nonlinear function y equals fx. Then x consists of this DC value and AC component, and this AC component, you assume this is the sinusoidal variation, and the amplitude of this sinusoidal variation is very small. Okay, then we expand this function in the neighborhood of this y, large y, in the neighborhood of this constant value y. So y equals y. This is DC value, large y, and y hat. This is also AC component of y. Then this is the fx, large x plus x hat, can be expanded based on this Taylor series. So this is the f evaluate at this large x value, and this is the first order, first derivative of this function, evaluate at x equals large x times this is the AC component of the x, and there are some additional terms, but they converge to 0. That means if you add all of them all together, this value is much smaller than this, okay? So you can ignore this. Then you just take this one and equate two expressions like this. So this is the input. It can be considered the input. Input is small signal variation, sinusoidal variation, or in X. This is the sinusoidal variation in Y, and the relationship between is just simply the derivative of this function fx evaluate at x equals large X. This is called the linear gain of this nonlinear relationship. Okay. So this is the first interpretation of linearization process, and this one is the second interpretation, which use the concept of the local slope. Okay. Assume this is the case. This x and this y is fx, and some nonlinear curve is here. So this is the nonlinear relationship. Okay. Then x is located here. So x is x dcx large X plus x hat, which is sinusoidal AC component. Then you project this into this nonlinear curve, then you can obtain the exact response by extending this line. But that is another analysis. That is the exact analysis. Okay. But we want to have some linear relationship. For that, we evaluate the tangential line segment at this point, and we replace this nonlinear curve with this tangential line segment, and we consider this is the local approximation of this nonlinear curve at this point. Okay, this is the DC operate point or quiescent point, and so we evaluate slope at this point, which is called the local slope, evaluated at x equals large X, and this value. Then relationship between this AC input to AC output is obviously this one, and this is the local slope is this one, and this one is exactly same as this. So this is the relationship, which is the same as this. So this is the linear gain, and this is also linear gain. They're the same, exactly same. Okay, and another interpretation of linearization is, I have one specific example for the simplicity of explanation. Suppose y equals fx, and this fx is x squared. So then you perturb this, you perturb y with y plus, large Y plus y hat, and you also perturb this. This is the dcx plus acx. This bar represents the AC, small signal component, which is varying in sinusoidal fashion in this example. Then you expand out. This is a simple expansion of this. Then you have this. Then this is the DC term. You are not interested in this term now. And this is the first order AC component. There is an AC component, first order term. And we have coefficient 2x. And this is x squared, which is second order term. So this can be considered very small because x hat is small, and the small thing times the small thing becomes very small. So we ignore this, and you are not interested in this. Then you equate this y hat to this, and the 2x is the small signal gain or linear gain of this nonlinear process evaluate at x equals large X. So you have another interpretation, and this, the first one, and the second one, third one, they are all equivalent. Of course, they produce the same result, and when you compare this, this one is the easiest to evaluate and the easiest to understand. Okay, so but it's good to you understand this and this, they are all the same. Okay, so this is the glimpse of what will come in the forthcoming lecture number 3. And in the lecture number 3, we'll first discuss the details about the switch model and the average model of this, and we will see the final form of small signal model, which will be developed this lecture and the next one coming after this. Okay, and then we will discuss the engineering details about this, the theoretical discussions about this, and the equivalence between them and the difference between them will be addressed. So finally, this lecture will address the one specific linearization process that will be used in the later part of this topic, which is part of the expansion of this nonlinear equation. So this is the easiest way of linearizing any nonlinear relationship. So this will be used to derive the small signal model of this PWM switch, average model of the PWM switch, or average model of entire converter. Okay? So now we move forward with the next slide discussing this, the small signal model, switch model, and linearization process. Start with this lecture slide. Somehow I'd like to repeat this because it has some idea and it will guide us what we're going to do today. So models of PWM switch. So this is the PWM switch. This is the SPDT switch, but we renamed PWM switch. And this is the buck case. Then buck case, this is active terminal, and this is passive terminal. So maybe A, P, common terminal C. Okay. Between A and P terminals, there is a input voltage Vs, and between C and P terminal, there is an inductor. So inductor is now considered as the current source. So it provides IL. So this is the generic equation or representation of PWM switch in operation. And this is the circuit equation for that. So this VAP, this one, and IC is continuous variable. So continuous variable is multiplied with switching function, which can have a value of 1 or 0 depending on this time period. So this is time varying variable. So when this is connected to this A terminal, this VCP is same as VAP. When this is connected to this terminal, VCP is 0. Same is true for this inductor current. So this is just the not mathematical, functional description of this operation of a PWM switch. Okay, but this is very convenient because with this you can average this equation, kind of equation, and this is the averaged model of this PWM switch. So it has the shape of form of ideal transformer, and the thing is the turns ratio is 1 to dt. dt is time varying, continuous duty ratio. So this is a time varying function, and the equation of this is this one. So this satisfies the equation of ideal transformer. That's the reason we are using the symbolic notation of this. Okay. So take a look at this. This is the VCP as a time varying variable is multiplication of dt and VAPT, which are both time varying variables. So this is a nonlinear relationship, and we have another relationship here, and this is the definition of this continuous duty ratio. This is the moving average of switch function evaluate with the window length of time period, and the window is sliding all the time. So this is a definition. Okay. This is also nonlinear equation, and in particular, this is multiple variable nonlinear function because there are one time varying variable and another time varying variable. Is they multiply together and generate this time varying waveforms. So it is called multiple variable nonlinear function. We're going to linearize this. Okay. So this is the result of linearization. So this average model is transformed to this form. So this is called the PWM switch. The guy first invented this. He named it as PWM switch. So PWM switch is proper noun. So there is only one PWM switch model in the world. The name of that guy is Multivariable. Okay, and it looks like this. There is also ideal transformer, but in here this turns ratio is 1 to D. The D is steady state duty ratio, and it has input variable of VAP hat, and this might be input variable. This is also input variable. It's kind of output variable. I don't know, but somehow they are related, this relationship, okay? And there is another variable, D hat is the small signal variation of continuous duty ratio, because we are performing the PWM function here and here, so there is additional AC variable which is emerged due to the PWM operation of this switch. So you have another variables, and this is a dependent voltage source and a dependent current source, and this coefficient comes from the steady state information of DC operating point of the converter. So that is the DC variable, and this equation of that. So later on we'll confirm this equation and this circuit interpretation are the exactly same. Okay. So from this circuit model, you can directly derive this equation. Actually, the guy, the Multivariable, he devised this circuit representation from this equation. Okay, so later on we'll confirm that. We go back to our business. So first, I'll discuss the linearization of nonlinear function for the general cases, and later on we'll focus the linearization of PWM switch. So first, let's consider this one. Y is fx and fx is x squared. So this is a nonlinear relationship, nonlinear function of single variable. There is only one variable here. Another equation is g is function of f, x, and y, and the equation is x squared y. So there are two time-varying variables. It's called the multiple variable nonlinear function. Okay, this is the case of our PWM switch. Okay, but first we focus on this single variable case. All right. So this is the general description of something, this linearization process, and I'll show you three different interpretation of linearization. All of them are equivalent. Okay, all of them are the same. First one is Taylor series expansion of nonlinear function. So let's consider single variable case first. So this is the single variable function, and x contains the DC component and the small AC component, and in particular this AC component, we assume this is sinusoidal variation with amplitude of xs, which is very small. Okay, so for the graphical illustration of this is shown here. So this is xt is x plus x hat, this one. Okay, this is x hat AC component, and this is the DC component. So this is the waveform, sum of this and this. Originally it was here, because this magnitude very small, it was here, and it is sitting on top of this DC value. Okay, you are considering this situation. Okay, and this is the Taylor series expansion of this. Okay, you already know this. Okay, and this series is converged always, and this is infinity series. So there is an infinity term, but after this, you add all of these terms, then they converge to very small number. So you can ignore this. All of them can be ignored, and just take this term. Okay. So this function at particular point, the x is large X plus X hat, then you evaluate f at with this DC value, and you evaluate the derivative of f with respect to X, then evaluate that derivative using this, and this is the small AC component of X variable, and you just take this term and this term and ignore this one and all of the following terms. Okay? This is called truncate Taylor series. So we are just taking this, and the assumption is this one. So this the difference between this instantaneous X and DCX, which is small signal X, is very small. Okay, this statement is same as this one. So, or you can say this variation of this X is very, very small, much smaller than DC component, something like that. Okay, so this is the same. This is the same expression. It's called the small signal assumption. I said this assumption is all around us when we are talking about the PWM converter. Without that assumption, you cannot do anything. Okay, maybe we need to use some technique for the nonlinear system, which is useless. Okay, it provides something, but result is so complex and no insight on the dynamics and absolutely no information about the design. Okay, so this is truncate Taylor series, and Y, this is Y, and X is X plus X, large X plus small x, DCX plus ACX. Same is true here. Y can be decomposed into DC component and AC component. Then we have this, and we just equate this one and this one. Okay, we just find the relationship between this and this. Okay, just forget about this DC component. We are only interested in this AC component. Then X hat is this one. This is suppose the sinusoidal frequency of sinusoidal wave is omega s, and this remain the same. The magnitude will be changed, and the relationship between this between the ACX and the ACY is given by this. This is the coefficient. This is constant. Okay, this is the derivative function evaluate at this using this at particular DC value, which is then result is DC constant. That is called small signal gain of nonlinear function of fx evaluate at this point. So this is very important. At this point, okay, one particular point, if you use x prime, this will be different. Right? So for this case, this small signal gain is this one. Okay, this is one interpretation. And another interpretation is this. I think I showed this you several times. Okay, this is the nonlinear relationship. Y equals fx. Okay, and x is this DC component, and the AC component is on top of this. So variation of x is this much. Then you can use this nonlinear curve, this point. This is another analysis. This is the exact evaluation of something. Okay, but we replace this curve with this line segment. Okay, this is a tangential line segment. Evaluate at this particular point. Then you extend this. Then you obtain this graphically or numerically. Then this is the input. This is output. So this is the slope of at this particular point. So again, we need this small signal assumption. This one. Then this is the slope at this point. This one. And this is the slope of tangential line segment at the operating point. X and Y. Okay. So result of this is same as this is the result of Taylor series. Okay. We obtain this from, okay, let me this is derived from Taylor series EXPA Taylor series expression, and this is derived from this graphical construction, so they are same thing. Okay, so Taylor series, truncated Taylor series expansion, and this one is the same thing. Okay, exactly same idea. All right, so this should be very small, because if this is very large, you will obtain this value and this value, they are different. So to secure the accuracy of this should be very small. How small? We don't know. Okay, we don't have to know. We don't care. Okay, you assume sufficiently small. So this is the second interpretation of linearization. There is another interpretation of this. Okay, this is the Taylor series expansion, but we are taking this and this, and this, right? So now forget about this. So we want to have this one. This is the relationship between AC input and AC output, and the gain is K. Okay, there is a many ways to evaluate this. One of this is this. Okay, because if you take a look at this Taylor series expansion, so only x hat occurs at this term. This is x squared, x cubic, something like that. Okay, we ignore this because this x hat is very small. Small thing times small thing becomes much, much small. So we ignore all of them. Then you have this one is the same as this one. Okay, so this is the general idea. So somehow we want to evaluate, we want to find out this constant k, which related between ACX and ACY. Okay, this is one example. Right? There is another example. There are many examples. Taylor series is just one example, but this example always works. Okay, so K is this one, right? And punchline here is this sentence: for simple algebraic nonlinear equations, simple algebraic means something like this: y equals x squared, y equals 1 divided by x, g equals x times y. Okay, this is called the simple algebraic equation, right? So, but this also applies to this something like this. This is transcendental function. I don't know, transcendental. In Korean, we call it 초월 함수. 초월 means exceeding something, so something special. But first you expand this to the Taylor series, and you just truncate part of the term of this, then you can do the same thing, but assume just this simplifications is obvious. Okay, suppose, okay, so then you have this relationship, then evaluate nonlinear equation of this one with the variables consisting of DC and AC component, and just relate the only first order AC component in each term. Okay, so for example, you have this, then y is transformed to DC plus AC, and x is consists of DC, this AC, and you factor this out, you expand this, then you have this, and you ignore this. No, not ignore. You are not worried about this. This is a DC term, and this is the second order term, which is very small. So you are only interested in this term. Okay, first order term of x hat, which is this, then this is the relationship. All right. So later on, I'll show that the procedure A and the procedure B is the same thing. Same thing. Okay, same mathematical operation, but here you just expand it out and you use the Taylor series. Okay, this one looks something, this one looks very trivial, but they are same thing. Okay, same idea, right? And this statement is important. This statement is true for the multiple variable nonlinear functions, because we are going to linearize the equation of average equation of PWM switch, which is a multiple nonlinear function. So this type of approach is applicable universally. So we'll be using this later, but you should understand the origin of that approach. So another alternative presentation is just evaluating the slope of this. So suppose you have this and you want to evaluate the small signal gain of at x equals 2, then you take the derivative of this, which is this, and evaluate this at this point, which is 4. Okay, so this is the slope of at this point. The equation is so obvious, so simple. Okay, so this we use the concept of the slope evaluation, and this is the second concept. So we used y consisting of DC and AC. We used x consisting of DC and AC, and we expanded them out. So we just took this one and this one. We have this relationship, which is the same. Okay. The last one is Taylor series expansion at x equals 2. Okay. So this is the equation, and with this, and this is the y plus y hat, and this is evaluate with x equals x. Okay. Then differentiate these ones and evaluate that value at x equals 2, and put x hat here and evaluate this twice. So evaluate this again, and you have 2, and here 2 factorial is coming. Okay, but you have this x hat squared term, so you are not interested in them. So you just ignore this. Then you equate this and this. Okay, so this is 4. Okay, so you have the same conclusion here, here, here. So they are same thing. Okay, 3 different methods are the same eventually. Okay. All right. Then multiple variable nonlinear equation. Right. So same idea here. So Taylor series expansion of this one. So G equals fxy, and x has DC component and AC component. Same is true for the y component. And G evaluate with this one. So this variable has DC and AC component. Then first you evaluate that function with this, and you take partial derivative of this. This is a partial derivative using the chain rule. You know the chain rule. Okay. And evaluate that with this is the operating point. This is the first order term, because this is the first order of x hat. This is there is only one order y hat, and here this is squared, and forget about all high order terms, including this. Okay, so with this assumption, you ignore this, and you have this one. Okay. So this DC is DC, and you are interested in this AC component. Then this gain is K1, this gain is K2, and K1 is this one, this one. Okay. Evaluate at the same point. This is called chain rule, and this is evaluate with x is large X and y with large Y. Okay, same is true here. So in this manner, all right. Let me give you one very simple example. So this is our multivariable nonlinear equation, and evaluate the gain, x gain, small signal gain at x is large X and y is large Y. This is bias point, and you take partial derivative of this, and this is the solution. Okay, so simple, right? And so this is based on the Taylor series expansion, and this is just expanding out with all the variables contains DC and AC component, and you factor this out, you expand out this, then take just this first order term, and here this is the first order term, and this is the constant, right? So they're same thing. Okay. So eventually you will be using this all the time. Okay. You have nonlinear equation, then use the variables, all the variables, DC component and the AC component, and expand them out and just equate the first order term of both side. Then you have a small signal model. Okay, so they know this. They know this. Okay, though they don't know why they are doing this. Okay? It's the same as the Taylor series expansion and the same as evaluating slope. This is not easy to think about the slope because this is the two-dimensional things, three-dimensional things, but the idea is the same as the previous simple case. Okay? All right. We take 3-minute break here, and we apply the general procedure we studied in the previous lecture slide to our small average model of PWM switch. Then we'll obtain the small signal model of PWM switch. Okay? All right.